Hello everyone. So let's look at to one problem which deal with magnetic force. Let's say we are given a very long line current as shown here. So let's say this is our long line current which position along the z-axis, for example, and it has current flow in positive z direction, let's say I1, and then we have another loop or square loop nearby as shown here. Alright, let's say this loop, this rectangular loop, position with this d distance from the line current, and then it has a width, let's say about A, and then it has a height, let's say about B. So guys, this is actually from front view. If I want to draw the axis, actually this is along the Y, and then this is our Z, right? And for sure the x-axis will point out for just a dot. That's your x out of pitch. Alright, so this is our case, guys. So let's say the second loop here, we have the I2 which flowing continuously within the loop. So we have 1, 2, 3, 4 paths that the current flowing in. So now we are going to calculate or to find the force expressions that due to any source currents. So let's say I want to find the force that exerted on this rectangular loop, which due to the magnetic field from the line current I1 over here. So if you can recall, our last electric force can be expressed as shown here, is equal to dEq, right? So this is our previous equation of force that relate to the case of E field, whereby we are going to take a sample, any sample, and this is a force that exerted to that sample, and then guys, this field actually come from the other party, the other side, right? So again, the same thing for this case. Now we are dealing with magnetic field. So now we have, let's say, the dF for the magnetic field. Now we have again here, guys, this case we should take a sample or the element current, let's say IDL, right? It also could be your JS, DS also could be your JDV, right? That's our current element. Now guys, now we should have the next one over here. Here is our B, right? Okay guys, so to make it valid, this equation, we must add this operation cross, right? Because the output here is vector, and now we're dealing with two vectors, so we have to add this cross product to make it this equation valid. So guys, this is a force in electric field, and now this is a force in magnetic field. I guess I can just put H also can. So now we are going to use this equation of force to find the force actually exerted to this rectangular loop that due to this line current I1. Okay guys, so we know that from this equation, this B actually a source of field that come from the other party. It means that this B will come from this infinitely long line current. So we can simply find the guys, the B from here become the mu naught H1, right? So B1 from I1 current, which equal to, now we're going to have the H that due to very long line current as we obtained earlier. We know that the equation become the I1 over 2 pi r phi component. Okay guys, so that's the general equation for the H that due to infinitely long line current. So this B belongs or comes from this long line current because the source of field, right? So this guy's sample or element must be taken within this rectangular loop. So let's say, let's focus the first one. Let's say I want to focus on this first part. Let's say define as number 1, and this one has is number 2, and then this one is our number 3rd path, and this one going to be our 4th path. Okay, let's focus one by one. So let's say I want to find the force that exerted at this first line or first path. So let's draw in top view. I think much clearer to see the case. Now this is case of front view, which is from YZ plane. Now I'm going to draw again this case from XY plane to make it easier the view. So let's say if you want to look at from top view, which is on XY plane, you are going to look at this line become like a dot, right? Because flowing in positive Z directions, I1. And then guys, this line also will look like a dot because again the I flowing upwards, right, along the Z positive. So this is also your I number 2. Okay, so this is our axis that we focus on, which is Y, and now is your X, right? So this is your Z that pointing out, right, from the page, positive. Okay guys, so we also know that this distance has a D, so we have here a D. Okay, so now we are going to draw our B field or our H field that due to this I1 current. So based on your right hand rule, you'll know that the H will go in counterclockwise as shown here. Right, so let's say that's our H field, that or B field due to the I1. So guys, again, since this current or I2 actually positioned at certain point, so we have to find its tangential component of this B field. So let's say from this side we know that the I1 and I2 actually position along the y-axis, right? So we can simply find the the B field actually pointing this direction, right? The B field component. Okay, so now we know that guys, this B field against this positive X direction. So for sure this B field has direction of negative X. Okay guys, so guys, for this we know that this is our B, right? So this whole term guys actually refer to your B magnitude or B naught. And now guys, your field, this front field for standard 1, now we are going to look at this particular point, at single point. So at this point the B actually appear at negative X, so you can simply change this phi to negative X directions. Okay, so now we already know the B field at this particular point, and now we are going to substitute all this value into this equation. Right guys, so we know that guys, to use this equation we need to take a sample, right? This is our sample, so whereby this is our I2, where from this second rectangular loop, right? So now let's say I'm going to take a sample at this point. This is our sample, right? So that should be our current element as the I2 DL, isn't it? So now we are going to find the DF at this current element. So again, let's write the equations. This is our equation, right? DF. So let's have to find DF number 1. Right. Now we have to take DF number 2 at this polypoint. So add here, right, our DF. So now our sample here is I2 DL. So the I2 guys. Now what is our DL for this case? We can see from here this line current position along the z-axis. So we can simply change this DL become z dz. right? Because this current element actually taken from this line which position along the z-axis, so you can simply change the dl here becomes z dz. Okay, so and then cross our B field that we obtained earlier is shown up here, so that's our B field. So put inside your I naught I1 over 2 pi r. Okay guys, the r here guys means the distance that perpendicular measured from the source of H field to the point of interest or to your sample or current element. So this case our r here actually has value of d, so you can simply put here is a d, right? Because the sample or the current element has a fixed position which is at d from the I1 from the source of B field. So now the directions, since I shown here negative z x, so you can put here a negative x straight away. So that's the df equation. So now let's do a cross product between the z and minus x. So get from here you can have the answer become negative y. So make sure you use the correct analysis to find the output of this cross product. So you can simply proceed with the integration part. Sorry, the f number 1 that exerted in this first path. Can I have here negative y I1 I2 over 2 pi d integrate dz. Now guys, you can look at this sample, this current element, the I2 or for this path length actually has a limit from 0 to b, right? So that's our length of this particular path. So just simply put here the limit of 0 to the b. So if you proceed, you can have this equation, negative y directions. So the mu naught, so here mu naught I1 I2 b, right, after integrations, now over 2 pi d Newton. Okay guys, so this is our f expressions that exerted to the first path of I2 current over here. Okay, if you see closely, we have the direction in negative y. So by right guys, the f here that actually appear or exerted at this first pass become like a repulsive, attractive force that pointing in negative y direction. So that's our first force, or we can simply say that this is an attractive force. Okay, because attract to the other current source. Okay, so guys, if you proceed to the next part, I'm going to find the force that actually exerted to the second path over here. Is our second path, which from this limit, which is d, until d plus a. So that's the limit for the dl for second case. Again, let's draw in xy plane. I'm going to look at from top view of that case. So if you look at again in top view of xy plane, you can have again the source of I1 just like a dot as seen before. So that's your I number 1, and then guys, you can see that this length will have, you can see again this long straight line even from top view. So you can simply again draw the line as shown there, right? That's the length of the second path of I2. So here we have a distance of separation given as d, and then it has the width or the length of a, right? Okay guys, so again we need to take a sample or current element from this I2. So let's say this is my current element I took from here. So now we have the current element become I2 dl, isn't it? So guys, since this path actually position, you can see actually it lies along the y-axis. It's your X. It's your Z, which is out of page. Okay guys, since this path of I2 lies along the y-axis, so you can simply change this dy, guys. You can simply change this dy become y dy, right? And then we have this, guys, this distance, the sample distance with the source. Let's say we have to put y. But why? Because this sample can be taken anywhere along the line from this point to this point, so we have to put a variable. And now the sample no longer remain fixed, but it's become a variable of in terms of distance, so we have to put y, okay, because this y has limit from this point to this point. Okay, so using the same equation of force to find the force that exerted to the I2 second path. So let's say I want to find force at second path. I think, guys, we have to use the second current element, I2 y dy. Okay guys, and then cross again with your B field that comes from the first current. So if I want to draw from here our B field, you can see again the B field will pass through this sample, right? And for sure in that direction because the I is flowing in positive Z. So again, since this current or this current element positions at certain point from the current I2, so we have to find the B that actually exists at this particular point. Again, you have to find the tangential component of this B field. So simply you can see that the B actually appear as shown here. This is our B magnitude, and again the B now against the X positive, so we have to put a negative X direction. So that's our B field that actually appear at this particular current element. Okay, now so we have to put the B, which is obtained earlier, mu naught I1 2 pi. Okay guys, now the R again have to change to Y because now the Y is a variable because the distance from the sample to this current becomes variable, could be anywhere between this along this line, so we have to change to Y variable. Now here we have a negative X. Okay guys, again let's do dot product between this Y and negative X. You will have the output become positive Z. Okay, so let's proceed. The F, find the F2. So just integrate over Y, which we have 1 over Y here, right? So now we have positive Z directions, mu naught I1 I2 over 2 pi integrations 1 over Y dy. And again guys, the limit for the sample can come from this point, which is D, until that point, which is D plus A, right? So now we have a D down here and up here D plus A. So finally we have the F2 is equal to the Z direction positive mu naught I1 I2 over 2 pi. Now we have a line D plus A over D Newton. Okay guys, this is our second force that exerted on the second path of I2. So if I want to draw the force in your diagram previously, so this is our force directions in positive Z, right? So that is our force number 2. Okay guys, so if you proceed to the end, guys, you can see that the force that actually appear for the third pass will point that directions, which is kind of repulsive force, because if you redo again this same method or the same process, you're going to have the force F3 will have in these directions, and also this D, guys, we have to change to D plus A. Okay, so and also for the fourth one here, you can see that the force now becoming to the negative Z direction as shown here. The F number 4, whereby it has same magnitude as F2, so we can just simply cancel out this force because it has same magnitude but different directions. Now the only force that we have finally only due to F1 and F3, and the F1 has a negative Y directions, and then the F3 has positive Y directions. Alright, and then we know that the D here for the F3 become D plus A. So that's the only changes that you can find from your equation of F3. So if I want to write again the whole expression, the force that actually appear, force total due to force number 1, force number 2, force number 3, and force number 4. So we know that, guys, this force number 2 and 4 will cancel out each other because they have same magnitude but different directions. So now only have the force 1 and the force 3. So let's put down here your force 1 as obtained earlier, and negative Y mu naught I1 I2 B 2 pi D, and then plus the F3 here. Now it has positive Y directions, mu naught I1 I2 and B. Now here, guys, we have the little bit changes, which is now becoming a D plus A, because at this particular line it has distance D plus A. So that's the second changes for the F number 3. So here just change to D plus A. Okay, guys, so let's factorize the F expression that we obtained earlier. So now we have a force total that actually exerted on the rectangular loop line current, negative Y directions, mu naught I1 I2 B over 2 pi 1 over D minus 1 over D plus A. Okay, so Newton. Okay, guys, so that's our total or our final expressions of F that actually exerted or experienced by the second rectangular loop line current. So now if you are asked to find what is the force that exerted to the infinitely long line current I1, so we can simply use Newton's law, which says that the force that exerted between two parties, they're actually experiencing the same magnitude of force but in different directions. So in this case, we can find the force that exerted on the line long current actually is equal to the negative force that exerted on the loop current, right? So this is the force that we obtained earlier. So now we can simply find the force that experienced by the long line I1 current. So the F on long line current is equal to the positive, this whole term, and I have positive Y mu naught I1 I2 B 2 pi 1 over D minus 1 over D plus A Newton. Okay, guys, so this concept comes from Newton's law. Alright, guys, so I hope you can try yourself and make sure you really understand the steps in finding the magnetic force that exerted on any line current or any other types of current, right? So thank you and all the best for your study.